Hello everyone, welcome to my channel CyberTumb, and today we'll be discussing Cobalt Strike and we will concentrate on the Cobalt Strike infrastructure. Before I start with the video, I would like to say that I'm not promoting any products and services related to Cobalt Strike, and also this video is purely for training purposes. Okay, and let's start. Of course, we'll start with the Cobalt Strike overview, as probably many of you have heard about Cobalt Strike, but they don't know what is exactly, how it looks like. So this video aims to show you Cobalt Strike from a red team and blue team perspective as well. So what is Cobalt Strike? Cobalt Strike is commercially available penetration testing platform used by security community as well as wide range of threat actors. So Cobalt Strike was originally created for network defenders to train them to understand vulnerabilities and possible avenues of infections by cyber criminals. But saying this, that it is an adversary simulation software for this purpose and for red teamers and for training purposes, the Cobalt Strike has been stolen and actively used by a wide range of threat actors, from ransomware operators to APTs or advanced persistent threats. So Cobalt Strike is a command and control application itself. You'll see what this means in the next few slides. So Cobalt Strike has two primary components: team server and client. So the team server is basically a controller that accepts client connections, beacon callbacks, and general web requests. This is how the launching of the team server looks like. So we can see, this is a screenshot, by the way, taken from the Cobalt Strike training from Raphael Much, who is actually the creator of the Cobalt Strike. So we can see here we're starting a file called team server. This is the IP address that we'll be using, and the password. In this case, the password is the password. Okay. And this is basically how the user interface looks like. I'll explain this in a minute. But there's like two characteristics for the team server. First, it accepts client connections on TCP port 550 by default. I'm emphasizing by default. As you can see here, team server is up on 550. Of course, this port can be changed. And the second one is team server only supports being run on Linux systems. So you can't run it on Windows and on any other operating system apart from Linux. All right, let's move to the client one. So the client is how operators connect to a team server. Clients can run on the same system as a team server or connect remotely. So basically I can run the team server, and straight after that I can just launch the client. Of course, I have to start it from like a file. Like here, this is the example where the client's been run, and once you run the client, you will see this pop-up, which is the client connector, and here it will ask you information about the host, the port. You can add the port here. We can see again is the default port, and you will type the user. In this case, it's Rafi. As I said, I'm using the screenshots from the main training of the Cobalt Strike by Raphael Much. You can see the reference at the end of my video. And you add here a password. So the client can be run on Windows, Mac OS, or Linux system, in comparison, of course, with the team server that can only be run on Linux system. So that's how it looks like. Once you run the team server, once you configure the client and like you choose the username and the password, you will get this, which is the user interface. And you can start basically working on it. Here you can see that there are like 2 users that have joined, the Rafi, the first one, and the much. So let's carry on with the next slide, where we'll concentrate on this user interface. All right. This is how the user interface looks like. So the Cobalt Strike user interface is split into 2 parts. The top of the interface shows a visualization of sessions or targets. That's what we call sessions or targets. The bottom of the interface, this one, displays tabs for each Cobalt Strike feature or session you interact with. As you can see here, event log, first beacon, second beacon, processes, third beacon that we work on. So basically you can click on them and open like different tabs here. So to conclude, the Cobalt Strike provides a console to interact with beacon sessions, scripts, and chat with your team mates. Right, I mentioned a beacon session. Let's explain what is a beacon. A beacon is the name for the Cobalt Strike's payloads that is used to create a connection to the team server. So active callback sessions from a target are also called beacons. The beacon can do pretty much everything. So it can execute PowerShell scripts, walk keystrokes, take screenshots, download files, and spawn other payloads, like a lot of things. Beacon has 2 types, stager and stageless, so with one stageless. It's also called a full backdoor. I will explain this in the next slides. As now we'll concentrate only on the user interface. All right, so the Cobalt Strike has the ability to link multiple beacons into a chain, as you can see here. These are the beacons and they are linked into a chain. These linked beacons receive their commands and send their output through the parent beacon in their chain, this is like the first one. This is like the parent beacon. And this chaining of beacons is one of the most powerful features in Cobalt Strike. The pivot graph shows your beacon chains in a natural way. Each beacon session has an icon, as you can see here. The icon for each host indicates its operating system. You can see you have Linux, you have like Windows. If the icon is red with lightning bolts, as you can see the 3 ones, the beacon is running in a process with administrator privileges. A darkened icon, for example, indicates that the beacon session was asked to exit and it acknowledged this command. We can see here a dark icon, but this is just an example. The firewall icon represents the egress point of your beacon payload. So the egress point, you have ingress and egress. The egress means outbound is going out, in contrast with the ingress is going in. A dashed green line that you can see indicates the use of beaconing HTTP or HTTPS connection to leave the network. So basically we have different types of beacons that they use like different protocols. That's why they're called HTTP beacon, HTTPS beacon, DNS, TCP beacon, and all of these things. We will explain every single beacon in the next few slides. Also, a yellow dash line can indicate the use of DNS that leaves the network. We can see it here. An orange arrow is a name pipe channel. We can see here, we'll explain what is this, but you get the idea. We have different color for basically everything, and this is very useful for the operator just to know only by looking at the color of the arrow, for example, where it's red, purple, green, or whatever. Okay, so what else important? We have a session table. The session table shows which beacons are calling home to this Cobalt Strike instance. So here we will see external IP. Of course, this is internal because it's for training purposes, but you can see external IP address of each beacon, internal IP address, the egress listener as well for that beacon, also when the beacon last call home, and other information as well. Also next to each row is an icon indicating the operating system of the compromised target. As you can see here, based on the icon, you can see that there are different windows. As you can see here, even different architecture, which process the beacon's been using. You can see the majority is on DLL 32. This is the sacrificial process for Cobalt Strike. This is the default Cobalt Strike process that's been used. And other information you can see here. As I said, listeners, HTTP, HTTPS, we don't have HTTPS, DNS. So what type of beacons we use for the particular beacon session, and you can see the users, the computers, and more information, which is very helpful. What else? We have target table. It's pretty much similar. Target table shows the targets in Cobalt Strike's data model. The targets table displays the IP address of each target, as you can see, and the icon to the left, similarly from the session table, which will indicate the target's operating system. Red icon with lightning bolts indicates that the target has a Cobalt Strike beacon session associated with it, as you can see here. Alright, now when we know what is the user interface, let's just give an example. So we have again the user interface. What we can see here, we can see 4 Windows sessions chained together, and the parent one is the first one. This is the parent one, and here we can see a few tabs that's been open. So now we can see this beacon on 3720. That's the one, 3720, having the IP address 10.10.191. So we can see we established the connection to the parent one, and we can see the command being execute hashdump. And once we executed hashdump, basically hashdump is used to record the password hashes of the local accounts. And once we do this and we receive the password hashes, we can see the information within the credentials tab. So I just open the credential tabs from here, and that's what we can see here. Basically, we can see the information the users, the associated passwords, the source. So either it's from where it's coming. Either it's coming from the hash dump, or this is an example for Mimikatz usage where we use the login password, and you can see the password hashes from Mimikatz as well, and that's the source and the associated host as well. So that's how it looks like for red team perspective. Okay, all right, listener management and payloads, different types. So what is a listener? A configuration for a Cobalt Strike payload. So listeners are the Cobalt Strike component that payloads such as Beacon use to connect to a team server. So that's how we used. We have different options, and we basically pick one of the three types of listeners to connect to our team server. So let's discuss the first one. The first type of listener is called egress. It's a payload that beacons out of a network. So from if you want this type of payload, you have to use either HTTP, HTTPS, or DNS, as these are the only types of payload that are beaconing out of the network. They're egress type, going out. The second type is peer-to-peer. It's a payload that communicates through a parent payload. So here is self-explanatory, peer-to-peer. So we are connecting to another beacon session. We have two different payloads that we can use for peer-to-peer communication is SMB and TCP. Okay, we'll explain all of this in the next slides one by one. And the last one is alias. It's a reference to a payload handler elsewhere in another toolset. For example, Metasploit, as Cobalt Strike is compatible with Metasploit. So we can use a payload handler from like the Metasploit framework. That's why it says foreign. This one is also, you go to this is the external command and control. That's why it's called foreign. It's alias. We have a stager as well. We'll explain in details about the different payload, stage and stageless. But basically, a stager is an optional beacon payload. So if you want, you might not use it. It's literally like your preferences. Operators can stage their malware by sending an initial small beacon shellcode payload that only does some basic checks and then queries the configured C2 for the fully featured backdoor. I will give more information about this in the next slide. But before that, just to mention, as you've noticed, all the different beacon payloads are named under a particular protocol. This means that this particular protocol is being used for the beacon. And yeah, let's go on and see the next slides. So before to go and explaining every different beacon payload, I want to provide you with some information about the payload staging, what is it and how it works. Why beacon is in brackets? Because the payload stagings are in general not only for the Cobalt Strike and the beacons, and it is general, like these two types are the main ones. So we have the stage vs the stageless. The stageless is also called the full backdoor. So let's first explain what is the stageless, but actually again to reiterate what is a beacon. Beacon is the name for the Cobalt Strike's payload that is used to create a connection to the team server, and is also an active callback session. As we said, payload can do a lot of things like running like a PowerShell commands, executing keystrokes, and all of these kind of things. All right, so the The stageless means payload without a stager. Actually, what is a payload? A payload is an attack component responsible for executing a malicious activity to harm the target. Imagine like payload like a small, tiny program that we execute. So, stageless means payload without a stager. Victim is tricked into running stageless.exe, and an attacker receives a callback to their netcat, in this case is the netcat listener, over TCP port 1337. So there is no stager involved in the process. A stageless contains everything you will need to get a reverse shell callback, so with the whole program, the whole script. And because of this, the file size is typically much larger and the program is relatively complex compared to that of staged. Stageless payloads send the entire payload to the target at once and therefore don't require the attacker to provide more data. That means we have a variety of listeners we can use, such as Netcat, Python, Socat, and etc. And let's move to the stage payload, as now we know what is stageless. The stage payload is basically the other way around. And stage payload sends a tiny program called stager to the target, which connects back to the attacker and downloads the rest of the payload. In the screenshot, our victim is tricked into running a dropper, which beacons out to attackers to server to receive a second stage, which is then injected and executed in memory, which triggers a reverse shell callback, as you can see here. A stage payload has to beacon out to another device, basically. The initial executable is typically called a dropper. And to receive a second stage, it's basically beaconing out, and the second stage contains the complete program. Sometimes this may just be shellcode, other times it could be a completely separate module like Mimikatz. Stagers are necessary in some cases because the attack might have very limited space for payload content. A great example is using a PowerShell one-liner for lateral movement. In terms of Cobalt strike, there are some advantages of stagers. Some disadvantages of stagers, as they're more brittle, so stagers could crash. They're also easier to detect. For example, if you use a Metasploit stager from the Metasploit framework, because they're very good known, and they're nowadays easier to detect, as the content of the stagers are very well understood and any kind of memory scanner should be able to pick it up. There is no capability to clean this up out of memory or to obfuscate them as well. However, the advantage of staging is what allows to use the Metasploit exploit to deliver a Cobalt strike beacon seamlessly, and it also allows us to pass sessions to Metasploit framework. Okay, and now when we know what is payload staging, different types of beacon payload, let's move on to the first type of beacon payloads. We will talk about the HTTP and HTTPS at once, as they're very similar. As the difference is that the one of the protocols is secured, as you know. Okay, red team perspective. So the HTTP HTTPS beacon payloads, they are by far the most common listener types. Or you can see here how to create the HTTP beacon listener. So we have this window where we can add here on the HTTP host. These are the two IP addresses that are the redirectors. Redirector is one of the recommended mechanisms for hiding Cobalt Strike team servers, and involves adding different points which a beacon can contact for instruction when using the HTTP channel, basically. So these are the two redirectors, and now we have the payload or the beacon calling back to us via the two different redirectors. This is in this case the payload. I know it's the same IP address, but that's fine. We can add here as many redirectors as we want. As we said, it's a way to provide multiple hosts for your is a way to provide multiple hosts for your beacon payloads to call home to, and redirectors also aids operational security, as it makes it harder to trace the true location of your team server, which is great. As imagine the victim notice this connection and decided to block the server, and if we don't have like these redirectors, they will block straight away our team server, and you have to configure the team server again instead of just adding as many redirectors as you want and then hiding the real team server, which is absolutely great. And that's the purpose of the redirectors. We can see here on port 80. So once we configure this, we will have to use the type of the delivery. Here we use the scripted web delivery. You can add the URL path here, so from where the beacon has to be downloaded to be started. You can add whatever you want here. This is the beacon, the payload, IP address, local post, the listener, in this case the HTTP, and the type of the beacon. We want to be a PowerShell, but there is a drop down menu here, so we can use like a different one, for example PSExec type or whatever, but we use the PowerShell one. And once you click this, it will launch success, and you will see this one liner, which is a PowerShell command. We can't see the whole one, but you can see string, which is download string. You can see the IP address /b, which is the URL path, and this is on the victim. So because this is from training purposes, we just basically executed this command and see what will happen. But in a real case scenario, you have to somehow trick the victim, either like downloading, clicking on something in order to execute our payload that we basically created here. But anyway, imagine that the victim clicked and somehow executed this command, and what we will see here, we will see on our user command interface that we saw from the first slide. We will see the Cobalt Strike payload and how it works. We can see the external IP addresses, that in our case are the redirectors reaching out to the compromised host. I can see the type of listeners, the user, the computers, or the beacon session, and what has been used. I can see it's the PowerShell was the type is PowerShell, and when it last beacon out to the Cobalt Strike server as well. So that's what we can see. All right, now we know how Red Team basically create HTTP beacon payloads and how it works. Of course, there are so many features that you can explore from the different types and like what to do, but in general that's how it works. And now I want to show you from blue perspective. This example is not related to the previous one. The previous one we just show how we can create like a payload. But now I want to show you how HTTP beacon looks like from blue team perspective. So just as a reminder, here we're discussing the two beacon types, HTTP, HTTPS, that are egress, meaning that they're going out. And now imagine that we have a Cobalt Strike controller and it's running a web server on port 80, as we can see here. And we also have a process on a compromised target, and inside this process we have an HTTP beacon payload. So what the HTTP beacon is doing? It's beaconing, and it will connect the Cobalt Strike command and control server by performing a GET request. In this case, our GET request is search hello. So we have this internal IP address using ephemeral port, reaching out to external IP address that in this case is our Cobalt Strike server, and on port 80, and is performing the request search/hello. Okay, and we can see the server responded with 200 OK, which indicates success, and respond with some blob of data that contains basically this blob of data. It's encrypted, we can't decrypt it, but what basically is saying the victim IP. The victim IP is performing this GET request to the controller and is asking basically, hey controller, do you have anything that you want me to do? And the controller will indicate with 200 OK success that the controller received this request, and will reply with this blob of data, which basically contains tasks for the payload to execute. So tasks, any commands or anything that the server wants like this beacon payload to execute. So imagine we are on our user Cobalt Strike user interface, and we type on this particular beacon that the compromised host, we type who am I, and I want you to execute who am I, and the server will go with this encrypted blob of data containing the command who am I, as this is the command that I want the compromise, like the beacon payload, to execute. And what will happen? The beacon payload will say no problem, and it will perform again a request, but this time will be a post request, as the beacon payload will be sending something. So the post request will be, let's say in this case, is /bk, can be everything, and it will respond again with a blob of data. Again, it will be encrypted, and will respond with the output of the command, of the instruction that the server actually wanted in the first place. So here, who am I? This will be the output of the who am I. It will be sent to the server. So the command server can also be like, I don't want anything. I don't have to perform any commands. In this case, the beacon payload will go and sleep and will be quiet till basically the operator says, there we go, I want you to now execute this command and do it this and that. So that's how basically it communicates, and that's what you see normally on the HTTP beacon from like network perspective. As of course, if we look from the previous example here, and would expect to see something on a blue team perspective, we should be able to search from the PowerShell box. We should be able to see this. It will be, I guess, more likely it will be decoded, probably, encoded in base64, I guess, or depending how you configure it. Basically, so this is from like a network perspective, network artifacts, and if we look for the PowerShell, it will be host-based artifacts. But as I said, both examples are not related. So the next payload that I want to explain is the DNS Beacon Payload. But before that, I want to explain you what actually is DNS. And more importantly, how it works. So DNS stands for Domain Name System, and resolves names to numbers or resolves domain names to IP addresses. It's a protocol that converts URLs and domain names into IP addresses that computers can understand and use. This is in a nutshell how this is the simply version of how it works. So we're typing in our browser abv.com, and basically this query goes straight away to the DNS server, and we're asking the DNS server, hey, do you know where the abv.com is located and what's the corresponding IP address? And the DNS server will basically respond with the IP address. So let's see now with more details how actually it works, because it's not so simple as here. So imagine we're querying the site cybertump.com, and so once we perform the query in our browser, the browser or the OS couldn't find the IP address in its own cache memory, what they will do, they will send the query to the next level that is called the resolver server or the recursive server, or another name is the DNS local cache. The resolver basically is the ISP or the internet server provider, and this server is used to resolve domain names to IP addresses within a local network. So the resolver will check their own local DNS cache, much like your computer will do, and if there is if the domain is not cached, the query probably it should end here. So the resolver will send back the information and you say, yeah, I don't know, it's not in my cache, but let me ask the root server, which is the next one in the chain, and that's the root server. So the resolver will perform a query and will ask the root server, hey, what's the IP of the cybertump.com? The root server, or the top of the top, is the next of the DNS hierarchy. There are normally 13 sets of these root servers strategically placed around the world, and they are operated by 12 different organizations, and each set has their own unique IP address. If the root server doesn't know the IP address, they will return this information to the resolver and they'll say, I don't know, I have no clue. Go and ask the TLD server, and the resolver will go and ask the TLD server, which stands for top level domain server. This server stores the address information for top level domains such as .com, .net, .org, and etc. So we're asking, hey TLD server, what's the IP for cybertump.com? And the top level domain, unfortunately, will not know and will be like, I don't know, but I know someone who knows. And it will refer the resolver to the authoritative DNS server, which is the last and final server. It's responsible for knowing everything about the domain. So, the resolver will go and ask, do you know the IP for cybertump? And the authority server will finally tell us the IP of cybertump, and the resolver will tell our computer the IP address of cybertump. And that's how it works. It's not so simply just like that. Of course, if you have it in the query, it will just go back and respond with the IP address. And all of this actually happened within a few seconds. Like, can you imagine how just is like a huge information about this, and it just everything happens in a few seconds. So let's just recap all of this. Performing DNS query, first goes to the DNS cache, after that to the resolver, which is the local DNS, after that go to the root server, the TLD server, and the authoritative server, and of course this will go to the authoritative server if no one from the previous servers or it's not cache in our local cache, like the IP address. So if no one knows the IP address, it will go to the last one. But that's how it works, the DNS. So, by knowing this, let's move to the beacon payload, the DNS one. So, as we said, it's also egress. Similarly to the HTTP and HTTPS, it's also egress, so it goes out of the network. And that's the main purpose. That's how we can set the listener. Again, we're just using the beacon DNS. In our case, it will be DNS here, stage report, and we fill all the required information. But now, let's see how the DNS beacon would work. Compromise system here. We have the compromise system. It's very similar as the previous one. We have the compromise system. The compromise system will query for the specific site. In this case, it will be the Cobalt Strike server domain, which is 123profile.love.com. It will ask in the cache or the resolver. In this case, the local DNS, as I said, is the resolver. We will not have it not stored in the cache. We'll go and ask the root server, after that the TOD, which in this case will be the .com, with the .com extension, and after that you'll go to the authoritative server, which is the last one, and then the DNS will go and ask the server. In this case, is the GoDaddy server, as you can see here. The GoDaddy server will say that it doesn't know what's the IP address corresponding to this domain, but it knows a server that actually knows. And what we'll do, the local DNS server will reach out to the Cobalt Strike team server and will ask if it knows the IP of 1234.profile, and the Cobalt Strike server will pass the query. We'll check the identifier, which in this case is 1, 2, 3, and 4, and it will check if it has any task for this particular beacon payload. And if there is, it will respond with yes, I do, and it will send the response to the local DNS server, and the local DNS server will forward the response to the compromised system. And this is how the DNS beacon communicates. In this way, it will send data or receive data, instruction, or tasks. So, to sum up here, the DNS listeners establish session to their team server using DNS request for domains the team server is authoritative for. So in this case, again, it will go to the DNS cache, local DNS server cache, a root server, TOD, a top level domain, authoritative, and when here comes to the last one, to the authoritative one, it will basically be forwarded to the team server, the domain for the team server that is authoritative for. And that's how it works. And from here, it will check for any instruction, and it will go back to the resolver and to the compromised system. So now, knowing how this works, let's see a beacon payload blue team perspective, how it looks like. Again, this is just to reiterate stuff. I'm adding this screenshot. So here we have the request from internal to external one, post request. It's very, very similar to what we actually saw from the HTTP and HTTPS. Again, it's like it's an egress one. It's an egress type of listener. So here we can see how it's the internal IP is reaching out to the external IP address and is posting again a blob of data that seems to be encrypted and can't be decoded unless you don't have the basically Cobalt Strike like particular token to decode this, and this basically only the Cobalt Strike server will have access to this. So here we would imagine that because it's post request, it's sending the output of the instructions that have already been sent to the beacon payload. And now we are moving to the beacon payload type SMB or named pipes. So far we have discussed the DNS, HTTP, and HTTP that we know that they are egress type. This is peer-to-peer type. So beacon SMB. SMB is a bind style listener and in most cases often used for chaining beacons, and you see how it works. Bind listeners open a local port on a target system and wait for an incoming connection from an operator. The SMB beacon is a payload that uses named pipes, which is a mechanism for inter-process communication in Windows to communicate peer-to-peer. So basically, named pipes are used for communication between two processes. That's why it's called SMB beacon, as the communication is between the first and this second host. Here we have a Cobalt strike controller, this one. Here we have a compromised system that is beaconing back to the Cobalt strike controller. That compromised host actually, by using SMB, by using pipes, these are the pipes, can communicate and basically to other like beacons, like child beacon. So this is how it works. This is the initial, the parent beacon that can beacon to different internal other like hosts and can basically infect other hosts, create different beacons. This beacon can create a different one, and all the information can be passed from this internal beacon host to the main one, and the main one can relate all of the information to the Cobalt strike controller. Of course, it's very important here to notice. Here we use the beacon SMB because it's peer-to-peer, so it's connecting this host to this one, or this communication between two processes, this one on host 1 and this one on host 2. So here, because it's going out, we're using egress types of listeners, and we know that egress types of listeners are HTTP or HTTPS or DNS. So that's how we use it. Beacon SMB for peer-to-peer communication, internal one, when it has to go out of the network, we use the HTTP or DNS. This is how basically we create a listener. We use the pipe name. This is a default pipe name for Cobalt strike. Of course, here you can name it whatever you want, and you can create the name of the listener again here, just to be easier recognizable on your user Cobalt strike interface. So basically, that's your controller, Cobalt strike controller. This is the parent, the initial compromise host that can actually go using DNS to basically communicate with other processes, and these other processes communicate with other processes. So this is a great thing of DNS. Another thing that is really cool about, SMB, not DNS. Another cool thing about SMB beacon is that you can disconnect it from it and reconnect it to it from another beacon at later time, and in this way, the SMB beacon becomes like a backdoor to maintain control of the target, even though if you don't want to actively communicate to it all the time. So that is pretty much for the SMB. It's a very, very powerful beacon payload. So now I would like to show you, this is again for blue time perspective, threat hunting, detection, default Cobalt strike name pipes here. So you can see that these are the default one. For example, if there is a pipe status and something here, it's stager for lateral movement. if there is a pipe from 7 to 10 characters, it means that it's post-exploitation job, mimikatz, power pick or whatever, or default artifact kit. If we see this, which is most commonly used for AV antivirus bypass. Of course, as I said, you can change it to whatever you want, but we have a lot of attackers that are too lazy and they don't even bother changing the default settings, and they just stick to the default settings. This list of domain pipes can provide you with hints of other like machines, most likely also affected by intrusion. For example, your name pipe has the reference to machine names or IP addresses for post exploitation or any SMB beacon. All right. Here it's an example for already deobfuscated Cobalt stack payload, and you can see the type of payload, and it's this one, default artifact kit. We can see pipe, MSSA, 4-digit here, and dash server. So for that purpose, the attacker used this pipe. Of course, you never know, you never be 100% sure for what purpose, but if they're using like the default Cobalt stack profile, this is what this pipe should be used for. And yeah, that's it. Moving to the beacon payload TCP type. So raw TCP is a bind style listener and can also be used for chaining beacons. As you can see here, it's peer-to-peer, so it's very similar to the SMB beacon, as it can be controlled by a parent beacon, that can be a TCP beacon, an SMB beacon, or any of the ingress beacons. When you're configuring the TCP beacon, you get to choose the bind port, and you get to choose whether or not the payload is bind to localhost only, as you can see here. This option is very useful if the TCP beacon is used for localhost pivoting, like privilege escalation or moving to another context on the system. The TCP local beacon can be also used, for example, creating a session for another user, and you can see here some examples as well. And you can see like the payload, that is TCP in this case. You can see on the port, in this case, this is the Metasploit port 4444, which is used by default. So I don't have an example from a blue team perspective, but consider it's the same, similar to the SMB beacon. It's just the TCP one. And this is the last of the beacon payloads, external C2 and foreign. We'll cover both of them here. So the external C2 and foreign, these two listeners are less common, but they provide compatibility with other payload types. Again, here you can see other, the new listener, and how similarly you can create the listeners. You can choose whatever port you want to for the bind, and the payload, and the name, of course, of the listener. Okay. So external C2 listeners provide a specification that operators can use to connect to a team server with a reverse TCP listener. Reverse listeners connect back and establish an external connection to an operator instead of waiting for an incoming connection, such as with bind listeners. The external C2, or command and control, is a specification that allows a third-party program or toolchain to control a name pipe beacon, to read data from it and write back to the Cobalt Strike product. And with the external C2 listener, the third-party program has an easy way to get in the middle of Cobalt Strike communication and relay things back and forth. Is the idea behind the external C2. The only thing command control can do is receive data from a beacon and relay encrypt tasks back to it. It's not different than HTTP or DNS serves in terms of capability. You can see here how it works. This is the target and the attacker, and then that's basically the path, and you can see how the third-party client's been used here for the SMB beacon, and then it's being passed to the team server. As for the foreign listeners, they allow connection from Metasploit's Meterpreter backdoor to simplify passing session between the Metasploit framework and the Cobalt Strike framework. So that's how it works, basically. All right, malleable command and control. I haven't mentioned this, but this is probably the most powerful feature of the Cobalt Strike framework. So Cobalt Strike users control beacons HTTP indicators through a profile and can select either the default profile that I was talking about, default pipes, default like ports, payloads and everything, or they can use customizable malleable C2 profile. Malleable C2 profile makes Cobalt Strike difficult to detect. The profile specifies how the beacon will transform and store data in a transaction. This is one of the most valuable features. Is the ability to modify the behavior of the beacon payload by changing various defaults within the framework. An operator can modify the memory footprint of beacon, can change how often it checks in, and even what beacon network traffic looks like. All of these features are controlled by malleable C2 profile, which is chosen when starting the team server. The threat actor have the ability to change anything from the network communication like user agents, headers, default URIs, to individual post-exploitation functions such as process injection and payload authentication capabilities. And this is amazing because the malleable C2 profile is designed to evade security detection, and a single security appliance is not equipped to prevent a Cobalt Strike attack. Only a combination of security solutions like firewalls, sandboxes, endpoints, and software to integrate all of these components can help prevent this kind of attack. So that's why it's so powerful. This is the reference that I used to create this video, so please feel free to go and read more about Cobalt Strike. And this brings me to the end of my video. So thank you so much, everyone. If you enjoyed watching this video, please subscribe. If you want to see similar or more videos, please share, like, and comment. If you have any questions, just let me know in the comment section. And thank you so much. See you next time.